yesterday's homework. Here is the charge QA, 8 nanocoulomb, 3 is at the point A, and charge QB minus 10 nanocoulomb, nano means 10 to the power of minus 9, and separation between them is the charge QB is placed at the point B, separation between them is 20 centimeters. And here is the point B along the line join of the charges on the side of QB, point P, I would like to get the field at the point P. At point P is at a distance of 16 centimeters from the charge B, given in the problem. All these informations are given in the problem. Now, let us work out. Here is, look here, let us first of all identify the direction of the field. The field due to the charge QA, where QA is a positive charge, 8 nanocoulomb is plus 8 nanocoulomb, is it not? Then the field at the point is radially outwards if the charge is positive. Therefore, field at the point P due to the charge QA is radially outwards. It is EA bar. And the field at the same point P due to the charge QB, which is negative, is radially inwards towards the charge. If the field charge is negative, field is towards the charge. If the charge is positive, field at the point is away from the charge. Okay, along the line join of the charge at the point, radially outwards, radially inwards. Therefore, charge QB is negative. Therefore, the field EB bar is towards the charge QB. That is the direction of the field for a single positive charge and negative charge. Charge is positive, field is at a point, is radially outwards. Charge is negative, field is towards the charge, radially inwards. Okay, radially means line join of the charge in the point. Now let us work out EA and EB magnitude. Okay, EA is equals to 1 upon 4 pi epsilon naught modulus of the charge QA divided by distance. What is the square of the distance? Square of the distance is AP square. Okay, distance between the charge is at A, and I would like to get the field at the point P. Therefore, here R square, R is the distance between the charge and the point. Therefore, AP square, is not R square is AP square. This is R square, okay? R is the distance between the charge and the point. Which point? At what point you would like to work out the field? That point. Okay, that's equals to 9 into 10 raised to 9. If the charge QA is 8 nanocoulomb, modulus of 8 nano is 10 to the power of minus 9 divided by R is how much now? 20 plus 16. AP is AB plus BP. AB is 20 and BP is 16. Therefore, totally 36. No, AB is 36 centimeters. Centimeter is to be converted to meter. It is 36 into 10 to the power of minus 2 the whole square. Now 10 to the power of modulus of minus 8 by calculating the magnitude. Take the modulus here. Okay. It is 9 into 10 to the power of 9 into 8 into 10 to the power of minus 9 cancels each other because 10 to the power of 9, 10 to the power of minus 9. It is 10 to the power of 9 plus of minus 9, 9 minus 9, 0. 10 to the power of 0, that's 1. It cancels. 9 into 1 is 9. Upon 36 square, 36 into 36 into 10 to the power of minus 4. 36 square is 36 into 36. 4, 9 ones are 9 fours are. 4 ones are 4 twos are, 2 ones are 2 18s are. Therefore, the final answer here is, it is everything cancels in the numerator. 1 upon 18 into 10 to the power of minus 4. 18 is taken to the numerator, 1 by 18, that is work out to the value of 1 by 18, 1 upon 18. That's equals to 0.0555 like that. It is 1 upon 0.5555 means 0.06. Let us take it at 0.06. I'm sorry, 0.06 into 10 to the power of minus 4 is taken at the numerator, 10 to the power of 4. What it is? Newtons. Newtons per coulomb. Charge field, field, assignment of field is newtons per coulomb. So, but it is not in accordance with the, it is 0.06 into 10 to the power of 4. While expressing the big numbers in terms of 10 to the power. So this base number, this number should be within 1 to 10. Okay, 0.06 is there. You can even make it as 0. You shift it to the one place right. It will become 0.6 into right is shifted and minus. It is point is shifted one place right. Then it is 6 into 10 to the power of 4 minus 1, 3 newtons per coulomb. Okay. And similarly, EB, field at the point B, magnitude B, 1 upon 4 pi epsilon naught. It is into QB modulus of QB divided by distance between the point and the charge, point B, the charge at B, BP square, divided upon R square. R is the distance between the charge and the point. Charge is at the point B and the point is P, therefore BP, the distance R is equal to BP. Therefore BP square is 9 into 10 to the power of 9, 1 upon 4 pi epsilon naught value is 9 into 10 to the power of 9 into QB. QB is modulus of QB is minus 10 nanocoulomb. Modulus of minus 10 is plus 10. 10 into 10 to the power of minus 9. Why 10 to the power of minus 9? Nanocoulomb. Modulus is taken is 10 to the power of minus 9, what becomes 10 to the power of plus 9. Okay. So this left side number will become minus, will become plus. That's all. Okay. This minus will remain same. Index sign remains same in modulus. Only the left side, the sign, this side. Okay. That changes. Upon how much it is? BP square. BP is 16. 16 square. 16 into 10 to the power minus 2 the whole square. Okay. It is 10 to the power of 9. 10 to the power of 9 cancels. Why it is 10 to the power of 9 into 10 to the power of minus 9 is equals to 10 to the power of 9 minus 9 equals 10 to the power of 0. 0 that is equals to 1. Therefore, anything into 1, 9 into 10 into 1, that is 91. That's why. So, automatically cancels each other. Okay. And it is 9 into 10 is 90 upon modulus of charge is taken. The negative should not be considered. Negative sign should not be considered. Only positive value of the charge should be taken. 90 upon 16 square, it is 256. 16 into 16, 256 into 10 to the power of minus 4. 10 to the power of minus 4. Now 90 upon 256. Can use the calculator. During the what it is theory examination, you can use the calculators. Not allowed in CET. 90 upon 256 is equals to 0.035. It is 0.035 and 35 into 10 to the power of 4. Minus 4 is taken to the numerator. 90 upon 256 is 0.35. Minus 4 is taken to the numerator. It is plus 4. 10 to the power of plus 4. But it is newtons per coulomb. That's equals to, let's shift the point. Here is 10 to the power of 3. Let's have same in this case also. Let us have 10 to the power of 3 only. Therefore, point is shifted one place right. It will become 3.5 into 10 to the power of 3. 4 point is shifted right, then minus 1. Point is shifted one place right, then minus 1. Point is shifted one place left, then it is plus 1. 10 to the power of plus 1 should be taken. Okay, 10 to the power of 3 newtons per coulomb. Now it is EB. Now here, which one is stronger? EB is stronger. It is 0.6. It is 3.5. EB is stronger. Now E and EB are in the opposite directions. Look at the figure. Okay, that figure is by solving the problems of fields, it is better to draw the figure. Now E and EB are in opposite direction. E bar and EB bar. Whenever you are mentioning the direction, you have to put bar. Bar indicates the direction. Okay. The symbols E and EB simply indicates magnitudes. EB bar are in opposite direction. Opposite directions. Therefore, the resultant field E, when two vectors are in opposite direction, then the resultant vector is, if two vectors P and Q are in opposite direction, then the resultant field is R is resultant vector. Field is a vector, force is a vector, any vector between field or force, etc. The two are acting in opposite direction, then the resultant vector is R equals to P minus Q magnitude. When the two vectors are acting in the same direction, the resultant vector R is equals to P plus Q. Therefore, only for magnitude it is. Okay, direction is to be considered later. The magnitude of the resultant field, both the field acts at the point P, superpose, the technical word is superpose at the point P, combines at the point P, produces a single field. The magnitude, the single field is called resultant field. The magnitude of the resultant field at the point P is E, and E is equals to bigger minus smaller. Okay, E is equals to bigger minus smaller, that's equals to 3 point EB minus EA. I have given that modulus of EA minus EB, one and the same. Modulus is taken or bigger minus. Modulus is taken in the sense to get a positive value. So here also bigger minus smaller is taken, then you are getting positive value. Okay, because magnitude of any vector quantity is a positive number. So it is EB minus EA, that's equals to 3.5 into 10 to the power of 3 minus 0.6 into 10 to the power of 3, 10 to the power of 3 is common, into 10 to the power of 3, 3.5 is 2.9 into 10 to the power of 3 newtons per meter. What is the direction of the field? So when two fields are acting in opposite direction, the resultant field is in the side of stronger one. Which one is stronger? EB. Therefore, the resultant field is towards the stronger one, is towards EB bar. Means it is PB. You can give the direction for E bar as along PB. From P to B. Okay, from P to B, PB. Is it not? EB bar is stronger. When two vectors are acting in opposite direction, you can show the opposite direction like this also, or one and the same. My tip of the finger, that is the direction, indicates the direction, opposite direction, or like this. Okay. Therefore, opposite direction. At this point, the vectors or fields are acting in the opposite direction. This is one direction, this is another direction, and the resultant field is towards the stronger one. Means the resultant field is towards PB, because EB is stronger, therefore resultant field is coming along EB bar. Okay, towards the stronger side. Therefore, the resultant field E bar, conclusion, finally conclude. Therefore, the resultant field at the point P, the resultant field at the point P, E bar is equals to bar, whenever you are putting the bar, you must mention the direction, is equals to much is the resultant magnitude 2.9 into 10 to the power of 3 newtons per coulomb. When a bar you have mentioned, you must tell the direction. In the direction of PB, not BP. This form field E bar is in the direction of P to B. Is it not? In the direction of P. Okay. Now try some more problems. So actually in your textbook, NCR textbook, you won't get what it is, this type of problem. Too many problems are not there. Some logical problems are there. They are useful for CET examination or for thing. But you can refer one textbook. It's called BASCO, State Syllabus BASCO textbook. So before this NCRT, so one state syllabus BASCO book was there. You can get the old copies from the bookshop. In that one, good number of problems are given of this type. Okay. Or even Butser also referring the same what it is, textbook for problems. You can have the problems from your Butser notebook also, notes also. Too many good problems are given from that particular textbook, only BASCO textbook. But theory examination, only what are given in this particular textbook, only that nature problems will be asked for theory. For CET, say you have next theory of this field. Electric field lines. Electric field lines. Electric field lines. Look here, before defining what is electric field lines and what its properties, try to understand it. Let's try to have the imagination of the field line. Okay. So here is one positive test charge, say plus Q or positive source charge, say plus Q or even small q. You can, even though in the beginning of this field theory we have taken the source charge as plus Q and test charge as small q. Later on the source charge maybe can be represented by even small q also. Okay. Okay, here is the source charge. Source charge means which produces the field. Means every charge produces the field. We are interested in the field of this charge, the source charge. Okay. So we know that the field are radially outwards. Here the fields are radially outwards. Field is a vector quantity. The vector quantity can be represented by line segment. Look here. So here the charge is positive, means field is radially outwards. So at this point the field is radially outwards, represented by a line segment. Because field is a vector, no? E bar means it has both magnitude as well as direction. Therefore it is a vector quantity. So every vector quantity can be represented by a line segment. So here it is. At this point the field direction is like this, because radially outwards, and it is represented by a line segment. So it is E bar here. Okay. And at this particular point it is represented by a line segment radially outwards, but a line segment shorter than this one. Why shorter than this one? Because see, what is the formula? Magnitude of the field 1 upon 4 pi epsilon naught Q upon R square. R is the distance between the charge and the point. Okay, charge and the point. Distance between the charge. Here is the charge, here is the point. Here is the charge, here is the point. Distance between the charge and the point. Therefore, the field is inversely proportional to square of the distance. So for a given field, the charge 1 upon 4 pi epsilon 10 to the power of 9 into 10 to the power of 9 is constant. Q is fixed. Therefore, R varies from point to point. For this point, R is less. For this point, R is more. Therefore, the field strength varies inversely as the square of the distance. Means more is the distance, less is the strength of the field. Therefore, so we know that the vector quantity, when a vector quantity is represented by line segment, the length is to be taken proportional to the magnitude. More is the magnitude, more is the strength, then the length should be more. So as you move outwards, the field strength increases, because field strength is inversely proportional to the square of the distance. Means more is the distance of the point from the charge, then the field strength decreases. Therefore, so field strength decreases means magnitude of the field decreases, means magnitude is represented by a length. When a vector is represented by a line segment, the magnitude of that vector is represented by a suitable length. More is the length, more is the magnitude. That's why, so when you move outwards, the magnitude of the field decreases. Hence, so at the outer points, the length of the vector should be small. So at the third point here, a line segment, this line segment represents the vector field E bar, but the length should be small. Here, greater length. As you move outwards, field decreases, this magnitude of the field decreases. As the magnitude is less, then the vector, the line segment which represents that vector should be shorter in length. Okay, the line should be shorter in length, because its magnitude is represented by the length of the line segment. When a vector is there, and how much length is to be taken, the vector is represented by a line segment. How much length of the line should be taken proportional to the magnitude. Suppose A bar is given the magnitude of 30, suppose 1 centimeter is equal to 10 units, then this line should be 3 centimeters. Suppose another vector B bar is there and B is equal to 20 centimeters, 20 units. A is 30 units, then I have drawn a line segment of 3 units to represent this A bar. And suppose B bar is another vector whose magnitude is 20 units, then I have to draw a line of 2 units, because 20 means 1 unit is equal to 1 unit length is equal to 10 units, say 10 units of that particular vector. Suppose it is a force, then it is 20 Newton, it is 30 Newton, 1 centimeter is 10 Newton is taken. Therefore, 3 centimeter line is necessary to represent A bar, and it is 20 Newton means 2 centimeter line is necessary to represent this B bar by taking 1 centimeter is equal to 10 Newton. Therefore, as you move outwards, the strength of the field decreases because of this formula. E is inversely proportional to the square of the distance between the charge and the point. Hence, the smaller line segment is to be drawn. So, in all direction, field will not be in one direction, it will be in all direction in the space. Okay, as you move on, the line length should be smaller. Okay, these are the line segment represent the field E bar. Okay, as you move upwards, the length of the field should be smaller. The length of the field should be shorter and shorter. So like this. Okay, in all directions, field is coming. If a charge is placed in the space, it is not possible to represent the charge in the space. On the board only you are drawing, but you have to imagine it is in the space. So it is the charge, field is in all direction. Okay, radially outwards if charge is positive. Here is the charge, field is in this direction also, in this direction also, in all direction it is coming, and it is radially outwards. This is the pictorial representation of the field. Now, this pictorial representation of the field of a charge itself is called field lines. So these lines now can be drawn by, can be joined by a smooth freehand curve, can be joined by a line. You can join these quantities vectors. And these vectors we are joining, we are getting a lines. These lines are called field lines. These lines are called what? The field lines. That is the field lines. Okay, these vectors are actually acting along a line or joined. Then you are getting the lines. These lines are called as what? Field lines. Okay. So tomorrow I will give some definition of field lines. Simply definition of field line is it is a pictorial mapping of a field of a charge configuration. Of a charge configuration is not the field can be represented by lines or by curves. That lines or curves is called electric field lines, and that field lines are the what it is, curves in the space actually, not drawn on the board. Even though it is drawn on the board, it is actually curves in the space. And these properties of these field lines and the definition of field lines I will give tomorrow. The definition of field lines is the field lines is the pictorial representation. By picture we can represent the fields. The pictorial representation of the field around a charge configuration. What do you mean by charge configuration? It is charge configuration means it is a single charge or it is a multiple charge. So you know that single charge also produces the field, and even multiple charge also produces a field. That multiple charge produces a field. That field is called as resultant field. For the resultant field of multiple charges or the field of a single charge, we can represent these fields by curves in the space. Curves may be a straight line or even curved one also. Then this pictorial representation of the field of a particular charge configuration. Don't confuse what do you mean by the word charge configuration. If a single charge is there, then also we can call it as a charge configuration, or multiple charge is there, then multiple charge also produces a single field. That also can be taken as a charge configuration. Okay. Pictorial representation of a charge configuration, and it is actually a space curve. This curve, the field lines are the phase curves drawn in the space. Okay. Tomorrow I will continue that theory. Yeah.